right here. And this particular example using an explicit chiral center just shows in perfect detail how this changes to R and S. The previous example I did 2 pages ago was a cyclohexane ring. We didn't talk about R and S, but we did show wedges and dashes, but here shows the specific details if we do use something that has a chiral center. So, substrate. Tertiary is the best because it leads to carbocations. I said that the nucleophile doesn't matter. Another way to say this is that all nucleophiles are equal for, obviously, SN1, which is what we're talking about. The nucleophile doesn't matter, and all nucleophiles are equal, and this seems very counterintuitive because we spent a significant amount of time talking about what makes a good nucleophile for the SN2 reaction. But this is different now. We have an SN1 reaction, and the reaction proceeds by a different energetic pathway where we have our substrate, and I'm just going to call this a leaving group. I'll call it R and LG, and R will be like our tertiary carbon and our leaving group. And the leaving group leaves first, and we end up with a carbocation here, plus the leaving group, which is usually negatively charged. These are right here. And this is a very high energy process. When the nucleophile comes in, it's a very lower energy process here. And basically, since this is the tough step to make the carbocation, the second step, since it has a lower activation energy barrier, means there'll be no consequence of whatever nucleophile we have. Any pair of electrons we have floating around, as soon as it finds a carbocation, it reacts. So, due to the nature of the carbocation, it wants any electrons it can find. It wants to solve this problem that it's very, very high in energy and unstable. And the activation energy to get here is much higher than it is to get to the final product. And so any pair of electrons that comes along, it works. That's why water will be a good nucleophile in this reaction. Anything will work. And so we no longer have a nucleophile trend for the SN1 reaction. They're all equal. This is hard to wrap your head around, but we have carbocation. It wants any pairs of electrons it can find. It really doesn't care. Okay? So already we have a different substrate trend. We have something different happening with the nucleophile. Let's talk about the leaving group. The leaving group trend is exactly the same as for SN2. This is, maybe some of you are breathing a sigh of relief. Oh, good, you already know that trend. Maybe some of you are like, well, this is all confusing. Substrate's different, nucleophile's different, leaving group's the same. You just have to keep in mind that leaving group ability always matters. We want weak bases because they will be excellent leaving groups. Okay? To get that bond to actually break, whether it's SN2 reaction with nucleophile attacking or the SN1 reaction where the leaving group breaks, the trend is exactly the same. You need a weak base, otherwise it won't react. So things we love here are tosylates. Tosylates, we like Br, I-. If we can get water to leave, that's a great leaving group. And then those horrible leaving groups that are impossible would be things like hydroxide again, strong bases. These things will just simply never leave in these reactions. So the good ones are like tosylate, bromide, iodide. Water is a great leaving group. It's a terribly weak base. So this is going to follow that exact same trend we saw. So substrate's different for both SN2 and SN1. Nucleophile has something different. Thankfully, the leaving group trend is the same. So the knowledge you put into leaving groups holds. The substrate trend is actually quite easy because they're opposite of one another. So we can use that to our advantage at the end of today's lecture. Let's talk about the last criteria, the solvent. You notice I'm going through these much faster today than before because we spent so much time before working on these with SN2, so we don't have to define things as much. We have apolar solvents, no reaction. Same for SN2. We have two other kinds, polar protic and polar aprotic. Recall that the product had OH or NH groups in it. For SN2, this was our preferred solvent, the polar aprotic. Polar protic worked, but it was slow. We learned why. You don't need to know why, but we do need to know that this is the best for SN2 and this is slow. And this one doesn't work. SN1 doesn't work. SN1 preferred. SN1 slow. The polar protic and polar aprotic flip-flop for SN1 and SN2. And we'll talk a little bit about why this is right now. So just recall, this is for SN1, and polar protic is the best, and polar aprotic is slow. For SN2, these two are flip-flopped. So many of you like making study sheets. You've talked to me a little bit about this in office hours or via email or messages. So there's an easy way to make a study sheet for this. You just strike a vertical sheet of paper and just have substrate, nucleophile, solvent, leaving group, and just outline little tiny notes about this, and you'll see differences that'll be easy to understand. You'll see some differences that are a little challenging to understand, and you'll see some differences and similarities that are easy to rationalize. So for polar protic solvents, and we've been using water almost exclusively, and we'll keep using water. It's a poor nucleophile, but it reacts because carbocations don't care about the nucleophile. But let's actually see what happens when water is the solvent. Why is this preferred? Well, this group leaves, and we generate two species here. We generate a carbocation, and we generate Br minus, our leaving group. And this is a very high energy process. We're going from a nice stable molecule to a very high energy reactive carbocation, but the tertiary is the best one, better than secondary or primary, so it can happen. This particular molecule is very high energy, and to stabilize it, it's surrounded by water temporarily. Ultimately, water will react with it when a pair of electrons get close enough, but the dipole vector for water, the direction of its net dipole, puts net negative charge here, net positive charge here. This is the shape of its dipole vector if we sum up its two polar bonds, and it actually surrounds this carbocation, temporarily stabilizing. But water also, and protic solvents that have the ability to donate a hydrogen bond, this very, very special thing that we talked about a little bit in our last class when we were talking about solvents maybe 2 days ago. It's this very special type of weak intermolecular interaction. Hydrogen bond is the essential component in DNA, protein-protein interactions. You know there's a plus charge here at each one of these. And this particular bond, it's definitely not covalent. It's a very special type of dipole interaction, but we have this negatively charged species, and water surrounds it in such a way as to stabilize it. So it's difficult to break this bond. It's difficult to break off bromine, but when it does, this solvent, if it's polar and protic, all polar solvents can stabilize the carbocation, but polar protic solvents can also stabilize the leaving group. Okay? And so here we have the special feature is that both the leaving group and carbocation are stabilized by protic solvents. Okay, this is the key feature, that particularly the leaving group can get stabilized by a polar protic solvent. So I'm putting this in our notes so that some of you who want a higher level of appreciation for what's happening at a molecular level, students who plan to pursue science, at least chemistry, biology, biochemistry, much farther than our class together, this type of understanding will come in useful later. I won't ask anyone about this summer to draw pictures like this, explain this, predict this. That's not the point. For us, in our introduction to this, I know it's the first time you've seen things like this. It's just good enough to know that for the SN1 reaction, if we can identify polar solvents that are protic and know that they're preferred, that's the thing I need all of you to try to strive for and achieve in this rapid-paced summer course. Even during regular semester, this is the same level of understanding that I would want you to strive for. This is here for your edification, your future knowledge, your future study. But for me, there's nothing for me to ask you about drawing these types of things. Why is it that polar protic is better than polar aprotic? Simply, this is enough for us, but this is the why for those of you who are inquisitive enough about it. We have about 10 minutes here before I think it'll be time for us to take a break, maybe 15 minutes. And what we're going to start with, or wrap up this first session we have together today, is just putting side